Hi guys, I've got the lateral directional system matrix here, and I'm going to talk about doing the exact same thing that we did with the longitudinal A matrix, producing those phugoid and the short period mode, and then being able to recognize the frequencies and the damping of those modes through the eigenvalues and then comparing them to the graph. We're going to do the same thing with this matrix here. So in the worked example in the accompanying notes, let's just have a quick look at the lateral directional version of the stuff that we did. So here we go. Let's just remind ourselves. So we have our lateral directional system matrix. I've also printed out the eigenvalues in the example. And then what we're interested in are these aircraft modes. So we can see there's clearly something oscillatory occurring here, and one or two, maybe more, other modes occurring in this data. And we're actually going to talk about what these modes are and how the aircraft actually moves in these modes of motion. So let's talk about those. Okay, so we've got our matrix here, and we can find the eigenvalues if we wish, just using Python, using NumPy, but we're going to talk about the modes of motion. We sort of went the other way with the previous one. We're going to talk directly about the modes of motion for lateral directional. So, lateral directional aircraft modes. And I apologize in advance if I have to pause and record this lecture in a couple of chunks, but I've got a day of student advising, so I need to fit slots of this lecture in when I can. So remember, for longitudinal motion, we had two characteristic oscillatory modes. There was the phugoid, which is that long, quite low damped mode, can sometimes be unstable. And we also have the short period, which is a short, small duration, high frequency, highly damped mode. We had two oscillatory modes. For lateral directional motion, there are three characteristic modes of motion. Maybe technically four, but we'll talk about that. Three characteristic aircraft modes that you will see exhibited. Only one of them is oscillatory. The other two are non-oscillatory modes. So for lateral directional motion, there are three characteristic modes. We'll talk about them. We'll say one oscillatory, and this is called the Dutch roll. And this is one that should be stable for an aircraft to be certified, but can be made stable through the use of a yaw damper. And we'll talk about this mode and where it comes from. And then we've got two non-oscillatory. One of which is the roll mode. Sometimes you'll see this being called roll subsidence or roll subsidence. This mode is always stable. And is basically a consequence of the aircraft having some wings. And the other non-oscillatory mode is the spiral mode. This one can be unstable, and can be unstable in a controlled aircraft, in an aircraft that can be certified, but it can be dangerous because it can lead to the so-called graveyard spiral. And this is particularly dangerous, and we'll talk a little bit about this. So let's talk about these modes. So let's just remember what we should be expecting for our eigenvalues then as well. So for the eigenvalues for the characteristic equation, if these are our modes of motion, we should expect one complex pair. So a complex pair of eigenvalues for this one, and if it's got a negative real part, then it means it's stable. And remember, the damped natural frequency will be given by the imaginary part, and the the damping ratio is given by a relationship that's provided by the natural logarithm, effectively, of the real part, and we'll talk about that. I can't do that in my head whilst I haven't got it written down. So we're expecting one complex pair of eigenvalues for this one, and then we would expect each of these to have the roll mode, because it's always stable. This will be one real negative number. And then the spiral mode will be one real positive or negative number. So in total, we'd expect 4 eigenvalues to describe this behavior. So the complex pair and 2 real eigenvalues should lead to 4 total eigenvalues. So if we get the 4 eigenvalues out of a matrix, then we're fine. And this should sort of be causing a little bit of consternation for some of you, because we see here we've got a 5 by 5 matrix. So the characteristic equation of this matrix is going to be a 5th degree polynomial. So if this is our matrix, it's always going to be a 5th degree polynomial. So it will be of the form lambda to the 5 plus, let me just check I've got this right. Let's call this, I'm just going to think about how I'm going to talk about this. Oh, that's fine. Plus a lambda to the 4 plus b lambda to the 3 plus c lambda squared plus d lambda plus e is equal to 0. So it's always going to be of this form. But with the lateral directional matrix, we'll always find that this is equal to 0. So this whole system can be represented as lambda 4 plus a lambda cubed plus b lambda squared plus c lambda plus d is equal to 0. So we'll always find that for lateral directional motion we can factorize it. We can take out a factor of lambda, which means that we know that one of the eigenvalues, so associated with this quartic here, we have a quartic equation, therefore we would have 4 eigenvalues coming out of this. And we're going to have a 5th eigenvalue associated with this one, but the eigenvalue is simply 0. So what on earth does this 0 eigenvalue mean? I'll give you a moment to think about that while I sip my tea nonchalantly. I really want a mug with NACA on it and not NASA. So if anyone can find one of those, that would be amazing. Okay, the answer that you're probably yelling out and you're screaming out, something to do with the fact that this whole equation has nothing in the right-hand side, and it's because nothing is a function of the yaw angle. So this is just a representation of the fact the aircraft is able to change its heading. Okay, so it changes its heading, doesn't really care about which direction it's flying in. It's very poor English. But the aircraft equations of motion are unaffected by heading, so the aircraft is free to be displaced in yaw and it not affect its modes. as long as it's reached a new equilibrium value. Something is wobbling around my desk, and I imagine that's very annoying for you guys to hear, so I'm just going to see if I can find out what it is. There we go. I hope you guys realise that I do a lot of audio processing of these lectures as well to try and remove things like where I've dropped my pencil and it's annoying. I try and remove all of that. Okay, so this 0 eigenvalue doesn't represent an aircraft mode that we care about. The aircraft mode that this is representing is just the fact the aircraft can change heading, so we don't care about it. So here are the four eigenvalues that we care about. So these represent the 3 aircraft modes. So we have a 4th degree polynomial, so we should expect there to be 4 eigenvalues, 2 of which are the complex pair associated with the Dutch roll mode, and we're going to speak more about these modes. The other 2 are the eigenvalues associated with the spiral and the roll mode. So again, we can represent this. We can further change our expression to say just check I'm not reusing numbers here. No, I'm not. Letters, rather. So we've got our characteristic equation that we can represent like this. Again, this is just the fact that the aircraft can change heading. We've then got the spiral mode. So the eigenvalue associated with the spiral mode is just a real number. It's equal to minus e. The eigenvalue associated with the Dutch roll mode is equal to minus f. And then in this case, we can remember this one's going to be a complex pair. So we've got these modes here. So let's, again, I'm having to change the way I assess all of this because we're all online, so everything, you guys have got access to the world's greatest repository of information, and you've got free access to computers. So I'm not going to teach you guys how to do sort of reduced mode approximations for these that you can do in class, but let's have a look at how we can get these eigenvalues and how we can compare. So in the accompanying notes, there's the eigenvalues that have been calculated for the Boeing 747. So in the accompanying notes, let me just run everything in here because this is my working copy of the notes. Let's run it all. It's good when I'm nice and prepared for a lecture. Okay, so here's the lateral directional matrix that we've got using the Boeing 747, and then we've got the eigenvalues that come out here. So we'll say for Boeing 747, and this will become more legible when we're back on the blackboard in a moment. We've got one eigenvalue which is just equal to 0. One eigenvalue which is equal to minus 1.2286, and no no imaginary parts. We've got another eigenvalue, which is a complex pair. So we immediately know this is the Dutch roll, 0.08024 plus or minus 0.7420 J, and then the last one is another real only, minus 0.465, let's say. So these are the eigenvalues, again calculated using Python. These are the eigenvalues associated with lateral directional motion for the Boeing 747 again. So you guys have already done this for one of your assignments, so you should be able to do this. So for these eigenvalues, we can think about what they represent. So this one here is just the fact the aircraft can change heading. So we can ignore this eigenvalue. It doesn't tell us anything useful about the aircraft other than the fact that it can change its heading. This one here has to be the Dutch roll mode. And we can tell a couple of things about the Dutch roll. It is stable, and we know that because the real part of the Dutch roll eigenvalue is less than 0, so it's stable. And we can think about a couple of other things. We know the damped natural frequency is simply equal to 0.7420 radians per second, and we know that the natural frequency is the square root of these two things added together. So let me just do that using Python. 0.0824 squared plus 0.7420 squared gives me 0.7466 radians per second, and we see again that the system is slower because of this damping, so that's the natural frequency, and we can get the time to half amplitude. Well, we could, if you wanted to get the damping ratio, we would take this and we would then expand it out, compare it with the standard form, which is lambda Dutch roll plus 2 theta omega n lambda plus omega n squared. So we then compare it, and you'll end up finding that it's the product of these. We then can, because we've got the natural frequency, we can then determine what the damping ratio is. Damping ratio is not particularly useful in terms of characteristics, though, that we can deal with as human beings. So we tend to rely on the time to double or time to half amplitude. Because this is a stable mode, we have a time to half amplitude. So it's equal to minus 0.69 divided by minus 0.08024. Minus 0.69 divided by minus 0.08024. Okay, 2.93 seconds. And we could also determine the period of this mode just based on 2π divided by this number. So let's just check out what the period of the Dutch roll mode is. No, this is not correct. I had the wrong thing there. That number sounded a little small to me. I've done the square root of it because I've been lazy and I've used the same line in Python. Thought that number sounded a little bit small. It should be about double that. Okay. So the actual time to half amplitude is 8.6 seconds. The period of this mode is 2π divided by the imaginary part of the eigenvalue. Okay, so very similar number as well here. This is 8.5 for 7 seconds. So that's our time to half amplitude. So we'll find that actually within one period, we've nearly got to half the amplitude of our Dutch roll mode. So that's as much as we can sort of tell with this, but we'll try and see if we can compare these numbers to what we got in the figure and see if these numbers are correct. So let's have a look at the plots that we have for the aircraft. Let's bring one of these up. So let's have a look at this one here, which is the roll attitude. I'm going to zoom in over here. So we've got both the spiral and we've got the roll mode in the very beginning. We'll talk more about that in a moment. And we've got the Dutch roll mode here, but we can immediately see if we can get the period of this. So 10 seconds to 18 points. Well, that's about 18.4 seconds. Yeah, so we've got, it's about 10 seconds to 18.4 seconds is about 8.4 seconds, which is what we expect. So the period's correct. If we can sort of estimate, it's difficult to estimate the amplitude here because we've got this is actually the spiral mode, and we'll talk more about these modes in a moment. We're going to talk about what they actually are and how we can remove them. So it's quite difficult to discriminate these modes any further without really understanding what they physically are for the aircraft. So I didn't intend to go into numerically calculating those parts, and that was a misstep on my behalf, but we're going to come back to this in a moment. Let's just talk about discriminating between these modes. So we'll come back to this. We've worked some things out for the Dutch roll. We don't really know what it is yet, so let's talk about these modes and what they actually are. So we'll talk about them in opposite order. We'll talk about the modes. We'll talk about the linear ones first. So the spiral mode. Spiral mode is effectively a measure of the way that the aircraft will yaw when it's in a banked turn. So if an aircraft is in a constant banked turn, and this is a coordinated turn, the aircraft will have a tendency to yaw one way or the other, and this can be the consequence of receiving more lift on one wing than the other, and also due to the forces on the vertical stabilizer and on the horizontal tail as well. So if an aircraft enters a coordinated turn, which means that the resultant vector or the resultant acceleration is aligned along with aircraft z-axes, then whether the turn is one of increasing or decreasing radius dictates whether the mode is stable or not. If the aircraft has a tendency to yaw at the same time, this causes the aircraft to pull into a tighter turn, effectively to increase that turn radius or decrease the turn radius. So if we can think about, if we were looking at north and east from above, if an aircraft starts out in a coordinated turn, but the turn has a tendency to increase in radius, this will bring the aircraft into a spiral shape. This would be an unstable spiral mode. So let's just narrate these. Let's say this is XE, this is YE, and this is then the aircraft position with increasing time. To be unstable because the aircraft has this tendency to turn in a direction that makes the turn tighter and tighter. And what this causes the roll angle to increase, and it causes the yaw angle to increase. So those two things are coupled there. So the aircraft is having this tendency to, once it starts to turn, it continues to turn more. And that sort of is in line with thinking about how stability traditionally works. So similar to pitch stability, CM alpha, positive stability is if the aircraft is disturbed. If it pitches up, it has a tendency to go back down. So if the aircraft was unstable, CM alpha was positive. If the aircraft pitches up, it continues to pitch. So very similarly, in the spiral mode, this is a combination of yawing and rolling. So if the aircraft is unstable, once it starts to do those, it gets tighter and tighter and tighter. By contrast, stability in the spiral mode will be if the aircraft starts to enter this turn, and then it just levels out to a straight direction. This would be a stable spiral mode. We'll say that turn is started, aircraft has tendency to move into the turn or to turn away from the direction in which it was headed. The aircraft has a tendency to yaw or roll, or yaw and roll rather, back out of that turn. So with these two here, this one would be given by lambda spiral positive. This one here would be given by lambda spiral is negative. Okay, so this is what spiral mode is. Now we'll talk about the roll mode. In fact, let's just quickly talk about this again a second. Just some more characteristics of the spiral whilst I'm here. You can tell I've really had to change the way I'm teaching this course because I'm never quite certain where I'm going in a lecture because everything's changed this year. The spiral mode is slow, even though it doesn't have a frequency. It just means it's quite slow to either build up or increase. So this means it's got very low damping. So slow doesn't mean that it's got a frequency, so there is no frequency associated with this mode, it's just got low damping. Can be unstable. And when I say it can be unstable, this means that it physically is possible for this to be unstable on an aircraft, but for certification purposes, the aircraft would need to be fitted with what's called a yaw damper to stop this from actually building up in flight. So the aircraft must be modified through control, through feedback control. For certification. That's by contrast to the short period pitching mode. If that short period pitching mode is unstable for an aircraft, you cannot fix that on a civil aircraft with some form of feedback control. Now I'm making conjecture there. I haven't checked that out under FAA certification, but these modes are so very different that the short period pitch mode is bloody dangerous if it's unstable. Spiral mode, a pilot can deal with it because of the fact that it's slow. Okay, and say slow here. Now, this means that it can lead to quite large roll angles if left unchecked. And what this can do is this can lead to something called the graveyard spiral. And let's just change this. I'm going to put, rather than must be modified, let's say the aircraft can be, because I'm not too hot on the latest FAA or the FAA rules with this. Spiral mode can lead to quite large roll angles if left unchecked, and this leads to something very dangerous called the graveyard spiral. Okay, so the way that the human ear works, the way that we can sort of detect our orientation in 3D space, is due to a set of complex apparatus in our ears called the vestibular apparatus. The vestibular apparatus is a set of cilia inside your ear canals. It's got three sort of out-of-axis rings which can detect angular rates in different modes of motion. It's also got what are called otolithic detectors, which are able to detect your orientation in 3D space. So they can sort of detect linear acceleration. So they can tell when you are sat up or when you're pointed through 90 degrees. So if you are in a coordinated turn, your gravity vector is pointed downwards. So your otolithic detectors don't detect that you are in imbalance. So they think you're sat upright. But your vestibular apparatus, of which the otolithic detectors are part as well, the canals cannot detect angular rates below a certain threshold. So you can't detect an angular rate unless it's a large one. So your body cannot detect small angular rates. So a slow spiral in a coordinated turn a slow spiral in a coordinated turn will be undetectable by the pilot if they're not looking for visual cues. So if an inexperienced pilot is flying in a situation, say night flying, where they're not instrument rated, then they could be in a situation where the aircraft is in a spiral, and the aircraft could have an unstable spiral mode, and it's increasing and increasing and increasing, and they can't realise it because it still feels to them like they're sat straight up, and their ears are not sensitive enough to detect these small roll and yaw rates the aircraft happens to have. So the aircraft is in a tighter and tighter spiral, and they might not notice this until they really suddenly see, fuck, the horizon isn't level. Okay? The aircraft isn't level. Something's going wrong here. Or they might see the nose dip down because the spiral might have built up to the point the aircraft dropped enough lift, the aircraft suddenly starts to drop down. And in that situation, what the pilot will have may, in most likely, have the tendency to want to do is pull the stick back because the nose has dropped down and pull the stick back. If you're in a coordinated turn, then pulling the stick back just increases the lift on the wings, which increases the wing loading, which makes the turn tighter again. So if you pull back on the stick in the graveyard spiral, you just make everyone slightly dizzy before they die. Okay? So this is why the spiral mode, even though it's slow, needs to be quantified, managed, and known about by pilots because of this thing called the graveyard spiral. Okay, I'm not examining you on your inner ear detectors, but I will put stuff in the notes about that because I think that's fascinating. Okay, roll mode. Roll mode is, and we call it this roll subsidence mode, is just the tendency of the aircraft to stop itself from rolling. And we've already dealt with this a little bit. It was CLP. So this is our aircraft flying straight towards us. If we have a positive roll rate, P, this will always cause an upwash on the starboard wing and a downwash on the port wing. which will cause an increase in lift on the starboard wing and a decrease in lift on the port wing. So it will cause the aircraft to have a tendency to stop itself from rolling. So this is always stable. So it will always be it'll always be a negative number. It won't be small. So lambda roll is always less than 0, and it's always quite a big number. This roll is heavily, heavily damped. And because it's heavily damped, means that it's over after, usually, for the 747, I'm not really seeing any evidence of this after a second or so. So this is very heavily damped. And in fact, it's the duration of these and the damping that helps detect which is which. So if we've got the eigenvalues out of our matrix, we haven't talked about the Dutch roll mode yet, but we will do. We've got these two modes here, which can be, one of them is the Dutch roll, one of them is the spiral, and one of them is the roll mode. So the one that's very heavily damped is going to be the roll mode. So this one here has to be the roll mode. This one here is the spiral mode. And for the aircraft we're going to look at, we'll always see the roll mode has greater damping than the spiral mode. Okay, this is the easiest way to detect. Obviously, for some aircraft, this one could be a positive number, and you would know immediately this is the spiral mode. This one will always be a negative number. So if they're both negative, if that doesn't help you, you just rely on this one being a very, very, very short mode. So it's very heavily damped. This one here will be a number that's in general smaller. Formally, we should take these and we should determine the eigenvector based upon the matrix to see which modes they excite. I'm not going to teach you guys to go through that at this time because that's more of the sort of stuff you do for an examination written by hand. So I've got a student meeting coming up now, so I'm going to pause this and then I'm going to speak about the Dutch roll mode and we'll learn about that and then we'll do some numerical comparison of these modes to the data. Okay, thank you guys. I will join back shortly. Okay guys, we're back. Speaking about these modes earlier, I mentioned here the aircraft can be unstable, and actually I looked this up just whilst I was away. Something that I think I probably should have known and did know really, I just misspoke. This often can be unstable for real life aircraft, despite the aircraft being stable in all other planes. So there can be some modification made using control for this, but it's really something pilots need to be aware of because of this reason that we spoke about, which is the graveyard spiral. So we've spoken about the spiral mode and we've spoken about the roll mode. The roll mode just being basically the aircraft's tendency to actually damp itself in roll. Dutch roll is the one that's left, so let's speak about this. So Dutch roll is a combination of side slip, rolling and yawing, all in combination. Remember, we've got side slip, roll rate, and yaw rate. Okay, it's called the Dutch roll mode because the aircraft has this tendency to start to side slip. Let's put it facing the camera. Start to side slip means the aircraft has this tendency to go like this, and as it then reaches the equilibrium, has a tendency to go the other way. And so this aircraft enters this sort of almost looking like a figure skater, and apparently Dutch people are known to be figure skaters. I didn't name this one at all, so I didn't name any of these, but called so due to looking kind of like a figure skater. Doesn't make any sense. So it's an oscillatory mode, as we said, so it's oscillatory. And this then, its stability is then given by the real part of the eigenvalue associated with it. And again, this is the one that I may be slightly confused with the spiral mode. This one cannot be unstable for aircraft certification purposes. And let's remove this line up here about can be, no, let's just cross this out. Let's say this one cannot be unstable for certification purposes. And can be controlled through modification of a yaw damper. This was me misreading my crib notes up here earlier. This makes sense, and I should have thought about it at the time. The spiral mode is the slow, non-oscillatory mode, so a damper won't do anything for this mode at all. So we can't control this using a yaw damper. We can control the Dutch roll mode using a yaw damper. So let's think about the mechanism that occurs during this. So if the aircraft has got this, we can always think about, remember, the weathercock stability of the aircraft means that as it enters if this is the velocity vector coming towards the aircraft, if the aircraft has this tendency to, if the aircraft goes into a sidestep, then the horizontal tail will cause the aircraft to have this tendency to return. So it's got this, what's called weathercock stiffness. Weathercock is one word, looks a lot ruder if I write it as two. So we can think about that for the aircraft, then as our aircraft is then the vertical stabilizer acts as a spring, providing stiffness, and also, in addition to the other control surfaces, also acts as a damper. So the aircraft can have this tendency, once excited, to oscillate like this, and it's going to oscillate in yaw. So as it's oscillating in yaw, as this, let's just check, I can't work out what way, to you guys that looks like the starboard wing. To me it's actually the port wing on my aircraft, but to you guys it looks like the starboard wing. It will, no, it doesn't look to you guys like the port wing, this is correct. Okay, so has this tendency to, as one of these goes forward, as the aircraft is, say, for example, yawing such that the port wing goes forward, we get an increase in lift on this wing, which causes the aircraft to then roll, because it's got an increase in lift here and a decrease in lift here. So as the aircraft has this tendency, if the aircraft is yawing, when it's, the faster that it's yawing will cause a roll, and then it starts to come back, and it has a tendency to roll in the opposite direction. So the wingtips are doing, it almost looks like it's doggy paddling in this sense, like a swimmer, but the wingtips are moving in circular motion. So they're going forward at the top and then aft at the bottom. So we see a circular motion of the aircraft wingtips. Okay, so we said here, as the aircraft oscillates in yaw, the wings experience an increase and a decrease in lift, and hence a roll rate is effected. That roll rate as well, if we think about the aircraft doing this motion here, so as what's causing the increase and decrease in lift, it's not the change in side slip, it's the change in the yaw rate R. And we'll actually see that the roll attitude and the yaw attitude are 90 degrees out of phase. So as the aircraft is starting to yaw, then as it's passing its 0 points, so say the aircraft is in this oscillation and it's been going at the point that it's at 0 yaw, the aircraft is at its maximum roll. And then it slows down, it starts to level off, and then as it comes back again, so when it passes its 0 point of the yaw attitude, that it's at its maximum roll in the opposite direction. Okay, so this motion, if we view it from here, it's very difficult to see because we've got combined side slip, yawing and roll rates. I'll provide a link to a video on the accompanying notes. It's probably the best way to look at each of these. So this is our Dutch roll mode. This is the easy one to spot because it's going to be the only oscillatory mode that we see. So we already know, we saw this here, that there was one oscillatory mode for the 747, quite lightly damped, very light damping in the 747. So what we're going to do now is we're going to look at the data for the 747 and see if we can do what we did for the longitudinal modes, which is tie up those data to the numbers that we got out. So in fact, let's go back to the eigenvalues that we pulled out here. These are the eigenvalues from taking the A matrix. So I'm just going to rewrite these on a new page because this page is getting very, very messy. So from the A mapped matrix, the eigenvalues, and we're going to neglect the 0, 1, R. So lambda, the first one is equal to minus 1.2286. The second one is equal to minus 0.0802 plus or minus 0.7420J. And then the last one is equal to minus 0.0464. So we can see from these what we said was this one's heavily damped, so this must be the roll mode. This one is oscillatory, so it has to be the Dutch roll mode. And this one here is the only one that's left. Okay, it's got less damping than the roll mode, so this one has to be the spiral mode. So we can look at the data and we can see if we can do exactly what we did. Remember, for the longitudinal mode, we were able to look at the modes are quite well separated. So the short period pitching mode doesn't really go on for a very long time, so it's easy to discriminate from the phugoid mode. And furthermore, they excite different states in the longitudinal motion, so it was easy to discriminate them. For the lateral directional equations, it's not so easy, because what we see in a plot like this is we see that something like roll attitude, we've got a combination of the oscillation, which has to be due to the Dutch roll, and we've got this mode here, which is the spiral mode. The roll mode we know is very, very short. So the roll mode, for example, up here, time to half amplitude is going to be tiny on here. In fact, we can just confirm this on here. So the time to half amplitude is 0.69 divided by 1.228. So we can see this is going to be a number. Well, we can see it's going to be a number that's about half a second probably. So what is that? I'll just do this for real. My computer responds. That'd be lovely. I've misplaced my calculator, which is why I'm having to use a Jupyter window to do basic numeracy stuff. Yeah, 0.56. So in 0.56. So the the roll mode is not really present in this graph because it would only be present up to about this part. So we see two modes here. There's some information that we can get from this graph. Let's see what we can get. We can use the peaks on here and the time between to get the period and get the damped natural frequency of the Dutch roll mode. So this is probably slightly easier to do on Python. We'll just pick some of these data off. Let me switch over to Jupyter. And again, I'm showing you this in Jupyter, but I would expect you guys to be able to do this from a graph if I gave you a graph. So this graph here is my roll attitude. We'll just pick out the data for approximately for the peaks here, and I'm going to write it on my graph, and then we'll come back to it. So at approximately 10 seconds, the peak is equal to 0.16. And then at a peak of approximately 18.5 seconds, then the roll attitude is 0.10. So we've got those data there. Let me just go back to this one here now. Nope, forgetting how to use a computer. Here we go. So I've just written those peaks onto this graph here. So we can immediately see that we're pretty good. We actually calculated on the previous page what the period was, but we'll just do it again here. There's only one of these that can have a period. So the period of the Dutch roll is equal to 2π divided by 0.7420, which I really wish I had my calculator. Well, I know it's about 8.5 seconds because I can see that on the graph, and from memory that's what we calculated it to be. But let's just confirm this. Yeah, we get 8.46. Okay, so which to one decimal place is the difference between these two peaks. So we've got t is approximately equal to 8.5. So that ties up nicely. So that's the only thing that we can get from this graph without doing some fancy stuff to it to figure it out. Because what we have present in the longitudinal, sorry, in the lateral directional modes that we don't have in the longitudinal, is that we have an overlaying of these two modes together. So if we were to try and use the peaks of what is very clearly the Dutch roll mode here, these are the peaks of the Dutch roll mode, to get the damping ratio, we would get it wrong. And that's because present in the data is this decay due to the spiral mode. So we see this spiral mode still reducing in this graph here. So we can try and see if we can work out some information. It will help us, and I've included some values in the accompanying notes that help you go through this. And I've sort of done this almost completely programmatically. But let's see if we can work this out. So what we need to see is there's some sort of exponential function that represents the spiral mode now. So the spiral mode is now this exponential decay that starts out at a value which is intercepts at about 0.19 and then exponentially decays until it reaches some value at, let's say, 50 seconds. And we can pick that off. This is the point whereabouts the Dutch roll has pretty much died off on this graph, and you can sort of estimate it. If I were to ask you to do this in an examination, I'd give you a much prettier graph with lots of discrimination and with grid lines, so you could determine it, but I'm going through this example where I've got access to the data as well. So we can then take this point of the data and actually over here at 50 seconds, we have 0.02, I think it was, yep, 0.02. So we can then estimate what that spiral mode is. Now, because we know that this is then an exponential decay curve, we then know that lambda associated with our spiral mode is going to be equal to 1 over t multiplied by e, sorry, not e, it's the natural logarithm of the decay between those 2 points. Because this is no longer present, this has no longer got the Dutch roll present in it, because I've estimated where this curve would intercept. I've just drawn on here and estimated it. So t here is there just 50 seconds. It's the final value minus the first value. And I've just had a student asking a question, would it be easier to convert things into imperial units? Probably know what my answer is to that. But we can then estimate our spiral value here. So then the lambda 2 is 0.02, lambda 1, 0.19. And if we estimate this, then I've included this in the accompanying notes. So if you estimate the eigenvalues, so 1 divided by 50 multiplied by the natural logarithm of 0.02 divided by 0.19, what this gives you is minus 0.04503, which is a pretty too precise really for what we're looking at. So let's call it 0.045. And that number is pretty close to what we actually get out of the data up here. Okay, it's harder to get these two out, and this is just me sort of drawing on the graph and estimating things, so it's never going to be that good. Now that we've got that, we can then remove the effect of the spiral on this graph up here. So we can appreciate, or hopefully you can appreciate, that if the spiral mode weren't present in this data, then the roll mode, or the Dutch roll mode rather, would be doing its thing here. I'm trying to draw that as well as I can, but if the spiral mode weren't pulling all of these data points up here, then the Dutch roll mode would be doing its oscillation around about 0. So what this means is that we can take these two values here and subtract whatever the influence of the Dutch roll mode is from both of them. So I'm going to say that the phi due to the Dutch roll is equal to 0.16 minus this exponential function that we've just created. And so we said this exponential, I never actually wrote it down, this exponential function, but this one here is the roll. So you've got a roll naught multiplied by e to lambda roll multiplied by time, where lambda naught is just the disturbance, which is that initial value that we said was 0.19, which is where it intercepted the curve. So then this value up here is going to be lambda Dutch roll, and that's going to be 0.16 minus 0.19 multiplied by e to the minus 0.045 multiplied by the time, which is just 10 seconds here. So that's going to equal, I've used slightly more precise values in my graph up here. So these numbers are going to be slightly different to what you get out if you put this into a calculator, but I'm going to put them on here anyway. So the numbers that you'd get out are going to be 0.042. That would be the value that this peak would achieve if the spiral mode weren't bringing this up. So this is then this would be the phi if the spiral mode wasn't there. And then we can do something very similar. We can say over here that the spiral mode due to the Dutch roll at this peak would be equal to 0.10 minus 0.19 multiplied by e to the minus 0.045 multiplied by 18.5 rather. And again, I've used slightly different values in the accompanying notes, so you guys can just check that if you want to see where these numbers come from. And we end up with a phi of 0.020. Now that we've got these two, we can then use it to confirm that we've got the correct part of the real part of the Dutch roll mode, and we can just do that the exact same way that we've done before. So we'll say that lambda of the Dutch roll, and now we're looking at the real part. That would be effectively representing this exponential decay curve that we would see around here. So we'd be trying to work out what is this exponential decay curve. And so that's therefore just going to be equal to 1 divided by whatever the change in time is, multiplied by the natural logarithm of however much the signal, or in this case the roll attitude, has decayed in this time. So the time difference is going to be 1 over, and for this it's just going to be 1 period for this example that we've got, which we said was 8.5 multiplied by the natural logarithm of 0.02 divided by 0.042. If you do this, you'll end up with a number that's pretty close to minus 0.87. Now, the number that you'll get from doing this equation here won't be the same as this number, because this number is taken from my worked example. I haven't got a calculator to hand, I don't know where it's gone, but the numbers are slightly different. Now, that's given in the accompanying notes there. Okay, so you can see how I've estimated those in the accompanying notes and where those numbers have come from, but we can just compare this number. This is the estimated real part of the eigenvalue associated with the Dutch roll, and it's pretty close. It's sort of 0.01 away in this case. We've got a slightly different number out to do with the way that, remember, I just estimated what this curve should look like and where it would intercept here. So if you made a better intercept of those numbers, then you'd do a better job. And let me just go and just show you where this is in the accompanying notes. This will be, I think this is updated, it will certainly be live by the time you guys read this. So what I've included here, and I've put here, getting eigenvalues from the graph data will make, this bit won't make much sense to you, watch the corresponding lecture. If we run this code, what it does is I've estimated where the intercept is here, and I put that value in. So right at the top here, I've said I've estimated just from by eye that intercepts at 0.19. If I change this to 0.12, for example, and run this again, you'll see that that no longer looks like a good curve that intercepts there. So let's put this back to 0.19. And again, you can see where I've made these sort of estimates here. So I started to use the same numbers. I said at 50 seconds, I picked up a value that looked like it was around about 0.02. If you want to do better, you can zoom in on here. So you can zoom right into 50 and see actually, well, there is still some oscillation at 50. So that estimation of 0.2, maybe a little bit high around here. I'd maybe even have a think to try and zoom into the graph somewhere where we can see that Dutch roll mode is completely not present in the data or reduced further. Oh, have I lost all my graph there? Let's reset. I would have a consideration to maybe, let's try again. I'd maybe consider looking somewhere like here and saying, yeah, there is less, for example, less Dutch roll. I'd maybe pick a point at 70 seconds and you could change and see what effect that has on the data about whether those estimated modes match what you get out of the data using this method. So it's harder to look at these modes for lateral directional because they are all collapsed in, well, the spiral and the Dutch roll tend to be collapsed on top of one another, so it's harder to get any estimates out of the data. But I've given you guys methodologies to do that, and I've included some examples in the accompanying notes. We've gone through this. This is about what I'd expect you guys to be able to do in one of these questions. I'm going to go through more examples using another aircraft in one final lecture this week. But what you need to be able to do, either from the A matrix of one of these aircraft, either in longitudinal or lateral directional, and in fact you should be able to do it in both, is to identify which modes are present, whether they're stable, what their time to half amplitude, if it's a stable oscillatory mode, or the time to double amplitude if it's an unstable oscillatory mode, what their damped natural frequency is, and what their natural frequency is. You should be able to determine those parameters and then comment on, whether that's, what sort of mode that is for the aircraft, whether it's phugoid, whether it's short period, and then conversely with the lateral directional do the same thing, whether it's Dutch roll, whether it's spiral, or whether it's roll mode, and tell me how you can determine those from the eigenvalues. And then what I expect you guys to be able to do is, on a graph of longitudinal modes, compare eigenvalues you get from the matrix with what you see in the graph. Are they correct? Okay, and the same for the lateral directional. If you get those eigenvalues from the matrix, I should expect you guys to be able to do the same for, this one here. Obviously you can't do it for the roll mode because the roll mode's too fast in these data, but I would expect you guys to be able to reproduce this sort of work. So we're going to go through another example using some data for a different aircraft. We'll look at the Piper Cherokee in an example that I'll record a little bit later tomorrow, and hopefully that will give you guys more indication of what I expect you guys to be able to do. Okay, hope you guys are having fun with this stuff. I love talking about this aircraft stuff. I think that I don't think people have a soul, but I think aircraft do. And if aircraft have a soul, it is the characteristic equation, and because everything comes down to it. It dictates everything about how the aircraft wants to fly through the air. So I'll see you all later in the week. I hope you're all having a wonderful week, and I hope you have a wonderful Thanksgiving, and I'll see you all in the next lecture.